harder to get them published, unfortunately. So it ranges from -1 to 1. If it's like a really big number in either direction, what's that tell you? Like say it's -0.8 or +0.8. It's a pretty strong correlation. So that means that there's like quite a bit going on between those two variables that they have in common. It doesn't tell us much more than that though, right? Like that if you look at, trying to think of two continuous variables, I don't know. So you're not necessarily going to know that that causes that. So why is it that a significant correlation doesn't mean that one thing causes the other? First of all, how would you be able to tell which one's which? Like which one comes first? You can't. Yeah, you can't tell. You don't know. You don't know which one comes first. We also, by the way, don't know that for a lot of our regression studies that we do. You could test the regression switching the IV and the DV, and you might get the same answer. You might not. You know, that's where your theoretical rationale for why you ask the question that you ask comes in really important there. But we have a number of studies, like we look at relationship satisfaction and sexual satisfaction a lot. Relationship satisfaction is significantly positively correlated with sexual satisfaction. Across the board, always, it just is. It's also bidirectional though. So there's not a huge amount of research that suggests what way that connection goes. And research that has done longitudinal work looking at this, including our lab, has not been able to conclude that it goes one way or another. So that means that and many times we've looked at the predictive value of relationship satisfaction to sexual satisfaction or vice versa. But we always say then in the discussion, it's very feasible that this relationship could exist in the opposite direction. But we chose to test it this way because of this in this particular paper, right? So you just have to have a rationale for why you're doing that. So yes, not a significant correlation does not imply causality. Also, a significant correlation is with how many variables? 2. So you can't really tell the causation of looking at these 2 variables, right? You would be pretty hard pressed to find 2 variables that you could say with certainty that this one thing causes another thing, especially if you're working with humans. Now, if we're working with other variables, maybe things that are a little bit more predictable than humans, sure, maybe. But I think everyone here works with humans, unless some people are working with rats. But they're still kind of unpredictable to control us. Okay. Good. That's the answer to question 1. What about number 2? Differences between Pearson product moment correlation, partial correlation, and semi-partial correlation. Anyone want to venture to explain the difference? What about this group over here? One of these. Are these 2 groups or 4 groups or 2? All right. One of you want to say what you found?
Not me.
They were looking at that question. So the Pearson product moment coefficient is the strength relationship between 2 variables, like 2 linear variables, so it's very specific to the linear, and then
specific to the Pearsons are. So yeah, it's specific to continuous variables.
Yes.
Yep, and there's only 2 of them. So that's a Pearson product moment coefficient has to have just 2 variables. It's looking at the relationship between them. Okay.
The partial correlation coefficient measures the association between 2 or more random variables once you remove the controlling variables. So you know where you
What's that?
That's all we have to that with.
Yeah. So that's correct. It's so that's essentially taking those 2 variables that give you a Pearson product moment coefficient and adding a few other variables that you're then controlling for. So you get a partial correlation coefficient when you are including more than 2 variables and you're parsing out the amount of variance that's accounted for by those other variables. So you can't do that with just a correlation. You have to do that with a regression. And that gives you that partial correlation coefficient. Did you find what a semi-partial correlation coefficient is?
It's a correlation between two variables and controlling to affect one or more predictors of variables.
Yeah. So actually the partial correlation and the semi-partial are pretty much the same thing. There's not much of a difference between those two. You might see that language used depending on the test that you're using, like if you're using a hierarchical multiple regression compared to like a stepwise multiple regression, but really not much of a reason to know the difference. But what it does mean though is just that it's not just two variables at play. It means that you're looking at the relationship between those two variables while holding some other variables constant. It can be just one other variable, or it could be like multiple other variables. You're holding them constant, you're controlling for them, and finding out what the relationship is between these two after considering all of these other things. Much more powerful test and a much more comprehensive way to be able to talk about your findings. To be able to say, after controlling for this, we still found this. Okay, what does R squared tell you? Yeah.
So
okay.
It's also known as the coefficient of determination.
Okay.
So it's like the most commonly used criteria for finding out how meaningful the correlation coefficient is.
Mm-hmm.
And it kind of looks at the portion of the total variance in one measure and explaining it by the variance that can be used to explain the variance in the other measure.
Right. Yeah. So to put that into like really applied terms, if you think about a regression, your outcome variable is a pie. Your predictor variables are all taking up pieces of the pie. If I had a marker, I'd draw this for you. I don't. It's taking up different pieces of the pie. The R squared tells you how much variance is accounted for in that pie by your outcome, by your outcome variables. So how much of that pie is being taken up? How much confidence do you have and in research with humans, especially research with humans where we're looking at like, variables like essentially like social type variables. That's what we look at a lot. You're not going to get an R squared value much higher than, 30% is great. If you can account for 30% of the variance in sexual satisfaction based on the variables you measured, you're looking really good. And that's so that's what it's looking at. It's taking how much variance of your outcome variable can you predict? What's the percentage of the pie that you're accounting for? So then that's telling you that you're measuring 30% of that, but 70% is unmeasured. We didn't measure it, we don't know. The other 70% are the other pieces to the puzzle that your next study can address, right? So we're all, and that isn't, that's not a bad thing. Like, it's okay that it takes multiple studies to be able to figure out what the pie looks like. You want that to be the case. Because if you just had one study that figured out the whole pie, your research question probably isn't that great and is not really asking a very complex or interesting question. So that's not the goal. The goal is not for one study to answer all of the questions with this, telling us about all of the variance that is accounted for sexual satisfaction. If we could figure that out, then I would be able to quit my job and open a business that tells people how to be satisfied sexually, but that just isn't realistic. That's not what we're looking to do. Okay, so good, yeah. So it's important to know this because we want to know what kind of an impact we have. Wow, you can account for 30% of the variance in sexual satisfaction by sexual communication. That's pretty great. How is multiple regression used to predict? So let's go with sexual satisfaction. So say we have a multiple regression model, we're predicting sexual satisfaction. How does it do that? In an applied way, you can talk about. What did you guys find?
Well, regression generally will give you a slope through the data that you have collected, and then you can interpret between the bounds of your data what a specific data point in your independent variable would do to your dependent variable.
Yeah, so you can look at, you could manipulate that and see how it would change, how that slope would change. If you want to think about it in a more applied way, coming back to that pie, what the multiple regression is doing is it's taking not just the two variables, right? Two variables are just used in that correlation, but it's adding more variables and saying, okay, and what you would always do is run bivariate correlations between the two variables. You always run a bivariate analysis of all of your variables of interest with your outcome variable. And you wouldn't include any that aren't significant at the bivariate level into the multivariate. So when I say multiple regression, I also mean multivariate or multivariable. And then under the umbrella of multiple regression or multivariate regression would be things like hierarchical regression. You don't need to remember all this, but like hierarchical regression or stepwise, or there's all these different ways in which you can add those variables. But it's used to be able to see like what of these variables are predicting pieces of the pie and how much of the piece of the pie is each one. So you can look at salience, like the most salient variable by looking at the beta value. You can tell like our most salient predictor of sexual satisfaction was sexual desire or was sexual communication. And in close second was, you know, whatever it might be. These are, multiple regression can be used in conjunction with all of these other pieces, so all of these sort of lead up to doing a multiple regression. Yeah?
We were talking about looking at like former stats of like an athlete, and so could you do multiple regression with that and then like look at maybe like last year's stats of all of their games?
Are those stats continuous variables?
I feel like they could be if it was like free throw percentages or like things like that.
Yeah. If you had one of those variables and you chose one of those, then to use, and it was continuous, then you could. You could also analyze that by looking at, by changing some of those variables into bivariate. So, sorry, changing one of those variables into a dichotomous variable. So like, yes, no on if they, I like really sports, not my thing. A yes, no, like they hit the, I don't know what they do, they hit the ball. Right, whatever the thing is that they do, that thing, if there's a yes and a no, you could also look at that. And that would just not be a multiple regression, it would be like a logistic regression.
Okay.
It's the same thing, it's just that your outcome variable is continuous versus dichotomous. Dichotomous being two categories.
Okay, but you have to have like, would you have to have multiple variables though, so you would have to take not just that one stat, like how often, you know, they make the free throws or the ball. So you have to have more than one.
If you want to do a multiple regression, you're going to have what are the variables that you think might be impacting how many free throws they have. And so like maybe you think that that has to do with their self-esteem. Maybe it has to do with their confidence in their free throw ability. You can measure all of those things, and you can measure those things continuously.
Right.
And then you can put all of those into a model to predict free throw percentage.
Okay.
And that's what you would use for the multiple regression. And then you'd be able to say that, oh, self-esteem is actually the most salient predictor of free throw percentage, so, and it's accounting for 28% of the variance in free throw percentage, so we should really make sure that we are talking to these players about their self-esteem and building up their self-esteem because that'll increase potentially their free throw percentage. I feel so sporty right now. So that'll do that for them, you know, which is pretty cool.
Yeah.
And this is where stats gets interesting, or this is what got me excited about stats anyway, is like thinking about my research and thinking about like, oh my gosh, we can answer like all of these really cool questions about sex and relationships using this. It's really neat. So I think all of you should sort of be thinking about like how this applies to your work and ways in which you could input those variables. Any other questions? Okay. I play softball. I play the softball league. I feel really sporty with that too. Actually, I do play sports. I just don't watch them. So I don't know much about all of that. But I was playing back catcher. And I have always, since I was a kid, called it back catcher, but I've always just like slurred the words and just been like, back catcher. Because I didn't know if it was back catcher or bat catcher. Turns out it's neither. It's just catcher. But yeah, so those are the types of sport things that I really mess up on all the time. But yeah, play back catcher. I'm really good at it. Okay, so let's start talking then about some of these tests. So correlation. We've already talked about this, but you're going to use this so many times if you're doing research. It's like the first stop. So my lab, we've been writing up abstracts for conferences, and I've said to them, okay, here are the data sets, run some bivariate correlations to see what variables are related that you're interested in so that we can get a sense of what kind of models we can build. That's not the best approach. What you should do instead is like go to the literature, come up with your theoretical reasons for conducting a study and doing all of these things. But I had already done sort of a theoretical background on a lot of this, which is why we did the study to begin with, right? So you can just go to the data, you can take a look at what things are related. And we talked about the range of that. So you're going to get an R squared. You're going to get an R and an R squared. And this will be significant or not. You usually don't bother looking at what the R value is unless it is significant. And on SPSS, it'll give you a little asterisk. It'll tell you, it's very simple to tell, but I'll show you that. Okay, so exciting. We are going to go into the t-test, ANOVA, and chi-square. We're going to look at the assumptions for each. We're going to look at the output for each. And we're going to look at the conclusions, and I'm going to give you an APA style, because that's what we use, and I don't know what you all use. Do you use APA style?